Hi everybody, welcome to we're in week 6 now. Crazy. So all of the year 12 students at the moment, you guys are two weeks away from your mock exams. So sort of finalize going through content this week and possibly, and then we'll probably look at some practice exam questions next week. There's Kai. Oh, I just like Kai and then he disappeared. So we're going to go through macromolecules, polymers, plastics, that kind of thing, and the production of them. So a big part of this unit is macromolecules. So you're looking at polymers of plastic, proteins, carbohydrates, and it kind of builds on the organic materials structure and function side of things. Just close. There's 27,000 tabs I have open. So polymers are what's commonly referred to as plastics. Plastics are referred to polymers one way or the other. It doesn't hugely matter. Can anyone tell me what makes up a polymer of any kind? The very simple answer. So Kai says many monomers. He would be very correct. So polymers. And sort of in this unit, they're referred to as plastics, but polymers are anything that's made up of many monomers. So we've got the main part about plastic is it's cheap, and for the moment it's plentiful. Does anyone know how we make plastics or what we use? Yep, but Ross, where do we get them from? So yeah, we get them from fossil fuels. So at the moment, plastic polymers are pretty cheap, very cheap to produce, but they will become less and less cheap as time goes on. So we remember polymers are made up of many monomers. So we join together thousands of smaller molecules in a process called polymerization. I want everyone to take 60 seconds and think of as many different polymers as you can. So 60 seconds, how many different polymers can you think of? So you should have been learning about some of them. So the two main ones are carbohydrates and proteins, as well as plastic polymers as well. So we have this process called addition polymerizations. So we can have up to 20,000 monomers and effectively a never-ending number. So we can go from ethene to polyethylene. But what we do here is we're getting rid of the double bonds. So we go from ethene to polyethylene. And say we react 10 ethene molecules together, we would then have this guy here, and then N would equal 10. All right, so shock horror, ethene becomes polyethylene, propene becomes polypropene, tetrafluoroethene becomes polytetrafluoroethane. So that's how we name it. That's all that means. We have an addition reaction that adds these ethene monomers together into a polyethylene segment. Okay. Here we have what's called low density polyethylene. It's made cheap and it's made nasty. You react ethene together to produce low density polyethylene. Now, I want everyone to take 60 seconds. And, okay, why is this called low density? That's the first thing. I want you guys to have a think. 60 seconds. Why is this called low density polyethylene? What about that picture there gives you an indication of what that might be? 60 seconds. Any ideas? Okay, so when we're talking about density in crude oil, just looking at the chat. Can everybody see the low density polyethylene picture? I'm not going mad, am I? Okay. So the density in polyethylene refers to how tightly the molecules pack together and the regularity in which they pack together. Again, I know this is a little bit of thinking time for you guys, but I'm trying to get you to think and then we discuss. So because we've got these really long branches and there's a low density, what kind of properties would you think would happen here? Do you remember back to the intermolecular forces of branched alkanes? Why would having significant levels of branching affect the properties of the polymers? Take 60 seconds to have a think. Yeah. So Ross has said the molecules can't pack tightly together, causing the dispersion forces to be weaker. So what do you think the properties of the plastic would be? Low melting point, yep. So just remember this. So Ross hit the nail on the head there. The presence of the branches mean that the molecules can't pack tightly together, which means the dispersion forces are going to be considerably weaker. So low density, soft, low melting point, non-conductive electricity. Do you think that there's plastic out there that can conduct electricity? So there's plastic that is so crystalline or so meticulously organized that it can actually conduct electricity. Okay, high density polyethy. Now we make it through this Ziegler-Natta catalysts. It's made using lower temperature, lower pressure. It's more expensive, it takes longer. But what do you notice about the chains? So the chains, as Kai said, are smaller. So what this means is that there's a higher density. The hydrogen atoms are closer together, so we have stronger dispersion forces. The plastic is hard because it's tough. It's the intermolecular forces holding it together are strong. So we're talking about something being crystalline. We're talking about the structure being very highly ordered. And we'll look through that when we go through the different kinds of polymers and the arrangements. So why would, again, if you all have a think for 60 seconds, why would adding to the carbon chain increase the melting point, increase the strength of the plastic to the point where we can use plastic to create bulletproof vests? So why would adding carbon atoms increase the strength of the plastic? So Kai says make it so so think simpler. The more carbon atoms there are, the more hydrogen atoms there are. The more hydrogen atoms there are, the more points we have where dispersion forces are interacting. More dispersion forces means stronger plastic. So the extent of branching is controlled by how we produce the plastic. You want to make cheap, nasty plastic, go right ahead. But it's not going to be that nice, high density polyethy. So crystallinity talks about how ordered the structure is. The more ordered the structure is, the more crystalline, the stronger it is, the more resistant to degradation it is. So, propene has a methyl group. So the arrangement of the methyl groups and how regular that is tells us the use we have for that particular polymer. So in isotactic polypropylene, sorry, they're not particularly ordered, it's completely random. Atactic, they are irregularly alternating. Again, take 60 seconds. What do you notice about the syndiotactic polypropylene? Mostly about the methyl groups. Just think what kind of pattern can you see? Can you see on the syndiotactic that they are regularly alternating one side to the other? What that means is that you will get them packed as closely together as possible. Just remember, propene has 3 carbons. So isotactic, they're all on this one side of the polymer chain. This means that they can pack pretty closely together, but it doesn't have the same crystallinity as the others. So isotactic, very strong plastic. Try and rip. I'll just show you back, but you won't be able to do it. It's made from recycled polymers. Atactic, they're randomly distributed all over the place, right? Not very good for anything, really. But syndiotactic, because they are on alternating sides, they create stupidly strong plastic. So there's a few polymers you need to be aware of. So polypropylene is our starting molecule. It's durable, it's cheap, it makes up most of our plastic. So tetrafluoroethene is Teflon. So nothing sticks to Teflon, and it also has a very high melting point. So we replace our methyl group and our hydrogen with 2 chlorines, and we get vinylidene chloride, which is food wrap or cling wrap, whatever you want to call it. We add a nitrile group and 3 hydrogens, we get fibers. Synthetic fibers, sorry. If we add a benzene group, we get polystyrene. We add a cyanide group and an ester. Whoever came up with that is crazy. But so plastic, I mean not plastic, super glue is a weird one. It's actually in its liquid form, it's a whole bunch of monomers. But the moment you expose it to water in the atmosphere, you end up with what's the word? It then starts to polymerize in the presence of water. Hence why it's a liquid. Change the cyanide group for a methyl group, and you get plastic. Oh, damn, I'm getting old. So I have an assignment due at midnight. I still got about 1,000 words to write. So, okay, I'm going to switch slides because there's a few more things I want to look at. Bear with me. A couple more slides I just want to show you. Thanks to Ross's teacher for these ones. So there's a couple of different ways we can produce polymers. So addition reactions are when we have alkenes. Condensation is where we have proteins and carbohydrates. And what happens is the OH group of one side reacts with the NH group or the H group of the other side as they come together. We get a carbon to oxygen bond and we expel water. So you can see that here. So we're just adding on with the alkenes, we're just adding on another alkane onto the end. So lots of high pressure, high temperature. Or the Ziegler-Natta catalysts, or titanium tetrachloride. So these just provide the energy in which the reaction occurs. So addition, polymerization are either prepared high temperature, high pressure, or with the Ziegler-Natta catalyst. This reduces the extent of the branch. So we start with an alkene and we end up with a massively long hydrocarbon chain. So ethene, propene, chloroethene, it is exactly the same thing. So I've kept these first, what, 5 or 6 now relatively short. And I did that because then it allows us more time later on in the term. You guys, it's 8 o'clock at night. I'm not going to take in a huge amount of content. That's all the content we're going to do. The next, what, 4 or 5 weeks, I'll probably do a couple of week sessions in the holidays as well, just to make up for some shorter sessions in the beginning. But we're going to spend now loads of time just doing exam questions. You guys are coming up to your mock exams. Next week, we'll go through a chemistry exam, and how to pick apart the questions, how to pick apart and figure out the answers. What formula do I need to apply where? How can I use my formula book to my advantage? How not to waste an obscene amount of time on your formula book as well. So I will see you guys next week. We'll probably do well over an hour next week on last year's exam. Whether we might have to spend a couple of weeks going through all the questions, how to figure out how to answer them, and then you guys are kind of ready for your mock exam. I mean, at the end of the day, mock exam means very little. Maybe I'm cynical, but there's a lot of stress and a lot of pressure placed on the mock exam. But how many of you have actually had your teacher take you through an exam question this year? Anyone? Yeah, no one. So you get to the mock exam and the teacher goes, oh, I'm very disappointed. And you should use the mock exam to figure out where you need to go. You can learn immense amounts of content in the next 3 months. Because it's 12 weeks of the chemistry exam, just over 12 weeks now. And you can learn a lot in that time. So that's what we're going to spend the next 5-6 weeks on, is making sure we got that exam prep down. And then once we start that, we can, I've got a few years worth of exams. I've got a few exams that I've written that I've used to prepare students. And that's what we'll focus on now. It's no longer about knowing the content. You can learn the content as we answer the exam questions. All right, I will see you guys next week.